the ARM v8M architecture was not the first ARM architecture that has introduced the ARM TrustZone concept. We have seen in previous slide that the ARM TrustZone is merely an answer to certain software requirements at design where we want to isolate and protect our sensitive and secret informations from the user-based application accesses. And to answer those requirements, ARM has introduced this TrustZone first of all on the application processors. To be more precise, this has been introduced on ARM v7A and then ARM v8A, even before getting introduced into this ARM v8M architecture. Then later on, with the evolution of those low power microprocessors, ARM had to introduce and import basically the TrustZone implementation to the ARM v8M architecture. The concept by itself is the same between both architectures, so it's answering those software requirements to protect our secret and sensitive informations from user-based application accesses. However, the way it gets implemented is quite different between the ARM v7 and 8A and the ARM v8M architecture. Why the implementation is different? This is due to the fact that on the application processors like Cortex-A, we don't have a restriction in terms of speed and frequency. So the frequency in the Cortex-A processors will be in terms of gigahertz. However, on Cortex-M microprocessors, the frequency will be in terms of megahertz. So it is way lower compared to the Cortex-A. This means that the switch back and forth between secure and non-secure state will have an impact on overall performance of our application. So on Cortex-A, this switch back and forth between secure and non-secure state, although it may introduce certain overhead, but this overhead will not have that big impact on overall performance because our processor is running on high frequency. However, in Cortex-M, this switch back and forth overhead for sure will have an impact because our processor or microprocessor is running on lower frequency. This is one of the reasons why the switch between secure and non-secure state in Cortex-A application processor will be done through a separate and dedicated exception level or mode. So in Cortex-A, if we are insecure or non-secure, we should always jump first of all to the exception level number 3 or EL3, and this one will be always in secure state. In exception level number 3, we'll have a secure monitor software, and this one is called as well a gatekeeper, and this one will be able to manipulate the security state of the mode that we are going to jump back to. So if we are running on EL1 or EL0, means exception level 0 or 1, and the security state was secure, then first of all we need to trigger a jump to the EL3. So this is This is 1, and this is the EL3. So we need to trigger a jump to this exception level 3. Then the secure monitor will manipulate certain bit within some control register to indicate the security state level that we are going to return to. And then the secure monitor can return back either to the EL0 or EL1, but the security state will be different. So we will be able to execute either in EL0 secure or EL0 non-secure. Same for EL1, either exception level 1 secure or exception level non-secure. So as you can see, the switch back and forth is going all the way through this dedicated mode. And of course, this will add a lot of overhead because we need to do kind of backup and restore of the different processor registers. However, this overhead, although it is quite big, but compare it to the high frequency that our application processor is running, is totally acceptable. If we try to migrate the same implementation to the Cortex-M with this lower frequency, then of course no. This additional overhead, which is quite big, due to the switching back and forth between secure and non-secure, will have a big impact on overall performance. And on top of that, will impact the real-time aspect of our Cortex-M microprocessor. And this is the second point I wanted to highlight here. The Cortex-A is an application processor. Hence, we don't care about this deterministic result. So we'll have a lot of cache memories, and this will impact this deterministic behavior. Deterministic means if we execute the software over and over, then we will get the same result within the same window of time. This cannot be respected in an application processor like Cortex-A. In Cortex-M, no. We want to respect this restriction, which is the real-time aspect. We should get the same result while running the same software over and over within the same window of time. If we try to implement the TrustZone using this flow or model, then for sure this real-time aspect will be impacted by the switching back and forth between the secure and non-secure state via this intermediate mode. So the context switching is always impacting the real-time aspect. Based on this, the implementation of the switching back and forth between secure and non-secure state has been significantly changed on the ARMv8-M architecture in respect to the previous Cortex-A processors. Here, the switch is memory-based one. So we'll not go through separate mode or exception level, and we'll have a light backup and restore basically flow when we are switching back and forth between secure and non-secure. In fact, our secure software will be running in secure memory area, and the non-secure one will be running in non-secure memory area. Here, the CPU will be running in secure state, and here the CPU will be running in non-secure state. We should just follow a proper jump that is predefined already within the ARMv8-M architecture from our non-secure memory area to the secure one, so that we trigger properly a switch of the CPU state to secure. Similar, if we want to return from secure to non-secure, then we should jump in proper way using the proper instructions from secure memory area to the non-secure one. And if we respect the usage of those instructions and the predefined conditions, then the CPU will switch back to non-secure. So we don't need to go through separate mode or exception level. We just do a proper jump from secure area to the non-secure, or from the non-secure one to secure. And then the hardware will take care of switching the CPU state.